In this final video, we're going to examine one more application of the t-test, and that's in an application that involves something called the paired t-test. And so once again here, whether it's a one sample, a two sample, or a paired t-test, all of these statistical procedures are based on the same student's t-distribution, which is specific to the degrees of freedom. But the paired t-test is used when we only have one group of research participants or cases, but that one group is sampled two different times on the same measurement. And so this is often also referred to as a dependent samples t-test because both sets of scores are dependent on each other because they're coming from the same group of research participants or cases. This is often referred to also as a repeated measures design from a research perspective because we're repeating the measure on the same group of people. And this type of design is ideal because it is considered to be more powerful. What that means in a statistical sense is that this type of research design, because we're comparing research participants to themselves, we're more likely to find a statistically significant difference if a true difference actually exists. The reason this is because when we compare people to themselves, the variability that inherently exists between people is removed. And so by narrowing the variance in the data, because the other factors that differentiates people between each other is removed, that will more likely produce a tighter distribution on the two different sets of scores and less overlap if a true difference actually exists. And so in terms of calculating the t-statistic, this is going to be a little bit of a different approach. We're going to use a table to do this. But what we're calculating is the t-statistic for the differences between the two sets of samples from the same participants. And that's going to be equal to the average difference subtract mu of d. Mu of d refers to the difference in both sets of scores among the population. And we're going to divide that by the standard error of the mean differences between the two sets of scores, where the capital letter D is used to indicate a difference. Now, in moving forward here to simplifying this equation, mu of D is always set to 0 unless stated otherwise. And so this is all tied back to the null hypothesis that we'll eventually get to, where we state that the differences between both sets of scores will be 0. So if we set mu of D to 0, then this term drops out in the numerator, and we end up with the average differences between both sets of scores divided by the same standard error of the mean differences. So just to summarize one more time, S subscript x bar d refers to the standard error of the mean differences, which is computed in a similar manner as we saw earlier, which is the standard deviation of the differences divided by the square root of the sample size. And so the standard deviation of the different scores will be evaluated, and the number of paired scores is going to be the same as the number of research participants. So the example here is we're going to ask the question of whether a particular drug, a new drug on the market, is effective at reducing tumor size. And so in this particular study design, it's important to understand when we see the word decrease, this implies a direction. If the question had the word difference in it, and did not specify increase or decrease, then we would go with the non-directional approach. And so in this particular study, 8 patients that were diagnosed with tumors were recruited, so it's a fairly small sample size. Pre-test measures were obtained of the tumors of the patients in this study. The patients were then prescribed a new experimental drug for 2 months, and then post-test measures of tumor size in the same participants were obtained. And so this chart here summarizes the raw data in tumor size. Here we see the tumor size, the pre-test scores. So patient 1 had a tumor size of 21 millimeters. After the 2 months of treatment, had a tumor size of 19. So we see a decrease of +2. +2, the difference is calculated as the pre subtract the post. And so we have a +2 unit, a millimeter decrease in the size of the tumor. We see in patient 2, there was no difference in size, and so the difference is 0. And we continue to do this for each of the 8 participants. And make note that there was one participant that had a tumor size measurement that actually increased by 1 millimeter. And so the first step here is to calculate these differences and then to sum the differences vertically. And so when we see these data, the question we're going to ask is if these differences that occurred among all the participants, 0 is still a difference, it's a difference of 0, but does the fact that one patient had the increase negate any statistically significant trend that might appear? And that's the point of doing the t-test. And so the first step here is to calculate the differences horizontally, and then we add up vertically, and we have a sum of the differences of +25. Moving on to our null hypothesis. The null hypothesis will state that the average D, the difference between the pre-test and post-test, will equal 0. And so the drug will not decrease tumor size. The alternative hypothesis will state that the difference will be greater than 0. So pre-subtract post will be a positive value because the positive value indicates that the tumor got smaller. We're going to choose a alpha level of 0.01 this time because we want a smaller degree of risk of committing a type 1 error. And because the question indicated that the study was looking for a decrease in tumor size, then we're going to apply a directional or one-tailed approach. We state the rejection rule. And so in calculating our degrees of freedom, which is 8 participants, 8 paired scores, subtract 1, we have a degree of freedom of 7. At the alpha level of 0.01, if we look this up on the t-table, we find we have a critical t-value of 2.998, which is quite a bit larger than some of the other critical t-values that we've seen so far in this unit. So the critical t-value is a positive 2.998. And so our rule here is that we're going to reject the null hypothesis if the t statistic that we calculate, we haven't calculated it yet, but if the t statistic is greater than or equal to the critical value of 2.998. We're going to retain the null hypothesis, basically saying that the drug was not effective if our calculated t statistic was less than 2.998. So coming back to our table here, recall that our first step was to calculate the actual difference from each of the participants or the subjects in the study. So 21 subtract 19 was a positive 2. Recall that our fourth patient saw an increase in tumor size by 1 millimeter. And so we add those up vertically. The next step is to create another column to the right-hand side where we're going to take the value in the difference column and we're going to multiply it by itself. So we're going to get a squared value. And all these values are going to be positive values, even for the -1. So -1 times -1 is a positive one. So we do this horizontally for each participant. We then add up, once again, add up all the numbers vertically to yield a sum of the d squared values, the difference squared values of 125. We then move on to actually now calculating. We start working towards the t calculation, but first we must calculate the standard deviation of the difference scores. And so the equation to do that is prescribed here as the square root of the summed scores that we had on the previous slide. So once again, here we see our summation symbol. We're going to add up all of the squared difference values. We're going to subtract that by the sum of the difference values. Once that sum is added up, then we square it, as opposed to squaring each value and then adding it up. We divide it by the sample size, and then we divide the whole quantity in the numerator by the degrees of freedom, and then we take the square root. And so what I've done here is I've substituted the numbers, and we come up with a standard deviation of the difference scores to be 2.59 millimeters. Once we have this value, we can then move on to the next step in calculating the standard error of the mean differences between the two sets of data. And we have what we had just calculated in part 1, the standard deviation of the difference scores, 2.59, divided by the square root of the sample size. Once again here, when we're calculating the standard error of the mean, we don't use the degrees of freedom because that was already addressed in the calculation for the standard deviation. So we square root the sample size, and we end up with a plus minus of 0.915 millimeters. In calculating the average of the difference scores, this is just simply adding up all of the difference values from the respective column in the table, and we divide it by the sample size. So 25 divided by 8 is that the 8 participants collectively had an average decrease in tumor size by 3.13 millimeters, and this is an average collapsed across all 8 participants. With these data now, we then go to our t-statistic equation, and we put our average value for the difference scores of 3.13 divided by the standard error of the mean difference scores, which we had in step 2 of 0.915, and we have a value of 3.421. That is our calculated t-value, t-statistic that we now want to use to compare it with the critical t-value that we had looked up previously on the t-table. So recall that our critical t-value was a value that was quite a bit higher than we had observed in previous examples at 2.998. And so at 2.998, this is a critical t-value that is a much higher standard for null hypothesis rejection. However, the calculated t-value of 3.421 was in fact found to be greater than the critical t-value. And so if that case occurred, as it did occur, we reject the null hypothesis. And by rejecting the null hypothesis, we therefore invoke the alternative hypothesis. In doing so, we conclude that the drug did reduce. We don't say a difference, but we say that the drug did reduce the tumor size in the cancer patients because that was stated in the alternative hypothesis. And in presenting these numbers, we would also add that the calculated t-value with a degree of freedom of 7 was equal to 3.421, and this was found at a p-level of less than 0.01. So this concludes this final video of our t-test unit.